with introduction of laser additive manufacturing and laser polishing, then conventional polishing methods. After that, in literature review, I have added few recent papers from which I took motivation to my work. After that, problem statement and objectives of my work. Then experimental setup, in which I will be covering experimental plan of my work. Then experimental setup which I have used. Then result and discussion of the work, and conclusions and future work. So uh, first. First is additive manufacturing. So additive manufacturing is the layer by layer a manufacturing process, as opposed to subtractive manufacturing process, or we can say as opposed to conventional manufacturing processes. When we come to laser additive manufacturing, in laser additive manufacturing, the laser is used as a heat source to melt the metal or whatever material we are using for fabricating our component. So additive manufacturing is basically used for building the components which are having highly complex shape, which is quite impossible or difficult to fabricate by the conventional manufacturing methods. Despite of this advantage, it has limitations, because it is having the defects like surface roughness, porosity and voids, cracking, vaporization of alloying elements. These defects are attributed to the stress trapping effect due to the overlapping. Sometimes the powder of metal may contain gas entrapment. Then uneven contraction, because of the rapid heating and solidification. Then some of the alloying elements may have lower melting of, we can say, vaporization temperature. So these may get vaporized at the low temperature than other elements. So if we consider this lamp components, of post processing is necessary. Here I have carried my study on polishing. So first we'll see what is the need of polishing. uh, the polishing is required for the aesthetic requirement of the components, prevent contamination of the surface, then remove oxidation from the component surface, then increase corrosion resistance, as the polishing will reduce the area of contact between the environment and the between area of contact to the environment, so that the corrosion resistance will reduce. Then improve the tribological properties like friction and wear resistance. Here is a comparison among different polishing processes. So mechanical, chemical and electrochemical polishing are the conventional polishing methods, and the laser polishing is the newly adopted technology. When we come to the geometry and the processing area of the component which are processed by laser polishing, we can see that the convention with the help of conventional polishing methods, we can polish the simple components with simple geometry and with large processing area. But with the help of laser polishing, we can polish the components which are having highly complex shape, and the area as small as in the range of less than 1 mm square. Also, the productivity of laser polishing is higher than the other polishing methods. Then the laser polishing can be fully automated, whereas other polishing processes are either non-automated, or the partial automation is present. When we see the environmental impact of this process, in mechanical polishing the abrasive grains are used, whereas in chemical and electrochemical polishing harmful chemicals are used, which are harmful to the environment. But in case of laser polishing, it is not so. Next is the skill of operator. For mechanical polishing, chemical polishing and electrochemical polishing, the quality of the polished product is depend on the skill of the operator. Whereas in laser polishing, if the parameters are properly optimized, the unskilled operator can also process the surface. So based on this comparison, I can say that laser polishing is the best choice for the precision polishing. Next is this is a typical mechanism of laser polishing process. So this diagram shows the laser macro polishing, which is carried out with the help of continuous wave laser. So macro polishing is carried out continuous wave laser, and micro polishing is carried out with the help of pulse laser. Here I am using this macro polishing because it is used for the components which are having the surface roughness greater than 5 microns. So we can see that uh, we can we can see that here is the irregular surface which is having some peaks and valleys, or we can say here is the some there are irregularities in the shape of peaks and valleys. So whenever the high energy laser beam is directed onto the surface, it will melt these peaks, and the molten material will flow into the valleys due to the action of viscosity and surface tension, and hence there will be the proper reallocation of the material, and hence after solidification we will get the more uniform surface. But as it is a high temperature process, there is a heat affected zone observed in the laser polishing. The process parameters considered in case of laser macro polishing are laser power, scanning speed, overlap, and depth of focus. My material under investigation is hastelloy-X, which is a nickel chromium solid laser polisher with high strength and excellent welding and forming characteristics. Because of these characteristics, it is widely used for the applications where high temperature sustenance is necessary. So the application shows it is used for the gas turbine applications, industrial furnaces, microchannel heat exchangers, and even some structural components also. This is the literature which includes a few recent papers. So here are the researchers who carried out their studies on the multipass strategy studies of laser polishing, whether the multipass strategy will reduce the micro cracks on the surface also or not. And then some of the researchers carried their study on the use of argon gas, whether it is beneficial to obtain homogeneous surface. Some of the researchers studied the effect of the pitch distance, that is hatching distance, or we can say overlapping, uh, effect of overlapping on the laser polishing. Here is the researchers who studied two major processes, that is formation of laser polishing surface includes the two major processes which are first is the initial properties.
Poonam,
Yes.
can you remember that I suggested something on the last presentation
uh,
regarding
sir,
authors' detail, how to write them?
yes sir, write only last name.
Then why a first name is there?
Okay. So actually I thought in literature you it's fine, only for references I have to give.
No, in always during your main presentation, wherever you are using it, it should
Okay.
be your last name, family name, and if multiple authors there, then you can write et al, or you can write the two authors by their surnames. Okay, using and
Okay.
at the last in references, you need to give complete detail.
Yes.
Continue.
Okay. So from literature what I have observed is the majority of work is carried out on the materials steel, titanium, and its alloys only. So if we see the Hastelloy-X, it has wide industrial applications for high temperature applications where corrosion resistance is also necessary. So I took Hastelloy-X as a material under investigation for laser polishing. Next is problem statement. Lamp components doesn't satisfy the aesthetic and tribological properties. Hence, these are not uh, applied for direct applications without post processing. So, the objective of my work is carry out detailed study on laser polishing of Hastelloy-X so that the process optimization and parametric dependence is carried out. This is the experimental plan. For the first step was selecting process control parameters. After that, experimental design using Takuchi's orthogonal array. After that, macro polishing with continuous wave fiber laser. Then I acquired the surface roughness values with the help of surface profilometer. Then process optimization and parametric dependence using Taguchi's method. After that, characterization of samples with minimum surface roughness, and then results discussion of the study, and after that conclusions and future scope. So this is the laser powder bed fusion setup which I have used for the laser polishing. Basically, this is the setup used for fabricating the components, but we deployed this setup for laser polishing. So this setup includes 500-watt laser system, gallows scanner which is used to direct the laser onto the surface as per our requirement, then build plate which is used to support the components which are rested on it, Then powder recorder, actually it don't have any use in laser polishing. Next is selection of process parameters and their levels. Selection of range of process parameters is carried out from literature survey. There are few researchers we have who have given the typical threshold range of these components. So the process parameters and their levels are selected as shown in the table 4. Next is qualitative surface analysis. As we know, any surface we can say something about its quality by just observing it. So these images are taken from stereo microscope to observe the to to observe the surface quality before going for further studies. So this is the as built sample. The surface roughness of it is 8.4 microns. It is quite dull and the scanning track marks are clearly visible on the surface. When we see the macropoly samples, the scanning track marks are still visible but in less, but in less amount. And also there is a burning of the surface, and burning of the partially melted powder is observed onto the surface. This can be avoided by using the argon gas environment, as argon gas shielding avoids the burning and oxidation of the surface. Next is the spherical cavities on the surface. These are due to the when the material is melted, some impurities get burned from the surface, and as the suction system was not effective, so these again fall down onto the surface. And while the polishing, these get digged out from the surface, and his spherical cavities are formed on the surface. Next is the quantitative surface analysis. It is based on the surface roughness measurement. So if we see the first sample, the surface roughness reduction is very minimum. It is only 4.13 percentage. But when we are going towards the higher power, in case of sample 7, at laser power of 150 watt, scanning speed of 300 mm per second, percentage spot overlap of 90 percentage, the percentage reduction is 32 percentage, which is better among all the samples. This is Taguchi analysis. If we see the laser power range is above the threshold value. Hence, the power is enough. The power range selected is enough for melting the material. Hence, there is a proper remelting and redistribution of material at all the three levels of laser power. But if we see, there is a slight peak at level 2. This might be due to the experimental errors, or as we know, laser lamp build components are not always homogeneous. So there might be some there might be some non-homogeneity in the sample, which needs to be investigated. Next is scan speed. When we are going towards the highest scan speed, the surface roughness is reduced, because at the lowest scan speed, what happens is the thermal ablation effect dominates over the thermal remelting. Hence the surface gets deteriorated than getting the surface finish. Next is the percentage spot overlap. If we see, in case what happens is when the spot overlap is less, there is a more gap between the two scanning lines, and hence the surface energy is not hence the laser energy, it's not enough to properly melt the material, and hence there won't be proper remelting. Hence when we go for the higher spot overlap, there will be the enough energy, hence proper remelting of the material, thus proper reallocation and proper distribution of the material. Hence uniform surface is obtained at higher spot percentage overlap. So the confirmation test, as we seen in Taguchi's optimization, the least surface roughness is observed at 150 watt, 700 mm per second, and 90 percentage of spot overlap. So we carried out the confirmation test to see whether these are optimum or not. So what we observed is the RA is 4.85 microns, which is least among all the values. So we can say that yes, this is the optimum value. Next is phase analysis using XRD. So in XRD, we can see that here is a at when we go for when we go from lower laser energy per unit length to higher laser energy per unit length, there is a generation of M6C phase, it is a phase which is rich in molybdenum and vanadium. And molybdenum and tungsten. And there is also generation of gamma prime phase, which is a phase having high strength. Here in as shown in graph B, there is a the peak shift is observed from laser energy per unit length to the uh, laser energy per unit length. This is because when we are going from lower energy to higher energy, what happens is there is a generation of high temperatures, because of which the residual stresses generated are high at higher laser energy per unit length. Hence there is a peak shift which is observed towards the right side. So the conclusions of this work is, for laser polishing, it requires very shortest processing time of the range of 11 seconds per centimeter square, which is the case of my study. Then glossy and smooth surfaces are obtained as compared to the as-built sample. The maximum, or we can say the optimum improvement in surface finish observed is 40%, which is at the optimized parameters of 150 watt 700 mm per second, and the overlapping of 90 percentage. In XRD studies, we observed that there is a variation in residual stresses. That's why the uh, phase shift is observed. The future work of the study, the laser micro polishing can be carried out after macro polishing to further reduce the surface roughness, because micro polishing is used for the samples which are having surface roughness less than 5 microns. Then here I carried out study on the flat surface, but we can go for the components with curved geometries, sharp edges, and the corners also. The further or detailed characterization can be carried out using SCM for surface topography, SIMS for oxide and carbide detection, then goniometer for evaluating the surface is hydrophobic or not, that is wettability studies. Then we can use electrochemical setup for corrosion resistance studies. So these are the few references that I have